Okay, so what we what we saw the last time was the Munk model. Okay, so linear bottom drag is now realistic. So what we did not get distracted by this. Linear bottom drag is not realistic. So what Munk did was adding this term. Okay. So biharmonic viscosity, lateral biharmonic viscosity, which makes more sense to put viscosity on a side wall, given that we find out that there is a boundary current on a side. Okay, so this is the Munk model. So we needed another boundary condition, and we chose the no-slip boundary condition. We got the same simple wind stress formulation in order to solve it analytically. We looked again for a solution which has an interior solution and a boundary correction. We did exactly the same thing, and we find out that this is the expression for the Munk model. Okay, slightly more complicated analytically, but what you get is a solution that looks like this. Okay, this is the Stommel model with the meridional velocity, and this is the Munk model with its own meridional velocity. So the difference here is not so much on the pattern, which is not realistic anyway, so you don't know which one is more realistic. But what is more realistic is the shape of the meridional velocity near the boundary. Okay? So here we added a boundary condition, and now the meridional velocity goes to 0 at the western side of the basin, and then it grows positive, and then it decays towards the interior. And the interior is dominated by a meridional flow, which is negative for this particular wind stress pattern. So for this subtropical gyre, which gives you an input of vorticity into the system, then the system wants to conserve vorticity, potential vorticity. It doesn't change relative vorticity, but it changes planetary vorticity. So it moves towards the equator to reduce F. Okay? So this is the large interior transfer. As you can see, the meridional velocity is small because it's the whole interior of the basin that is responding by moving towards the equator. And all of this mass is returned on a narrow boundary layer. Okay? So this is the Munk model, which is far more realistic in a way than the Stommel model. This is the original wind stress pattern that he used, and this is the flow, vertically integrated or homogeneous flow that he got. As you can see, we're always talking about isotropical gyre because it's the easiest example, but you can include a subpolar gyre as well, just changing the wind stress pattern. Okay, so you can get input of vorticity or removal of vorticity, and you get a different gyre, a different sign. Okay. What is the thickness of this boundary layer? We did the same scale analysis, and we reached a scale thickness delta, which is proportional to the horizontal viscosity and beta. Okay. So the main differences between the two is that one uses a linear bottom drag in the case of Stommel, and the Munk model uses a Newtonian harmonic lateral viscosity, okay, which is more realistic to add lateral friction. In both cases, the solution is the same, okay, because we're trying to approach reality. So the transfer in this view of interior is towards the equator for this particular wind stress pattern. So an anticyclonic wind stress curl. This vertical transfer is exactly balanced by a poleward transfer in a western boundary layer. That's because the boundary layer satisfies mass conservation, and it has to be a western boundary layer for friction to provide a force to oppose of opposite sign as the motion in the interior. We'll see a potential vorticity argument for that. So as I said the last time, friction is not the reason for a western boundary current. Friction is just a way of balancing vorticity, okay? But it's not the reason for the boundary layer. The western location does not depend on the sign of the Coriolis. You can do the same exercise in the southern hemisphere. Okay. It doesn't depend on the sign of the wind stress. You can get a subtropical or a subpolar gyre. You always get a western boundary current. But it does depend on the sign of beta. So if you make if you turn the Earth the other way around, then you will not get a western boundary solution, you will get an eastern boundary solution. The two thicknesses are slightly different because one assumes a linear bottom drag, whereas the other one assumes a harmonic viscosity, lateral viscosity. But roughly for kind of realistic values, you get a boundary correction of something like 60 or 100 kilometers, which is more or less what the Gulf Stream width is. Okay, then I told you the story of the first chart of the Gulf Stream, okay, which is definitely not what it looks like. Okay, and that's because there's this famous sentence that I don't remember. I don't remember the famous sentence. It was something like, absence of evidence. Absence of evidence is not evidence of absence. Did I say this already? Yes, okay. So absence of evidence is not an evidence of absence. So the fact that they didn't have observations, they concluded that something didn't exist. So they didn't have observations of the Gulf Stream and just a few fishermen saying it's a warm, narrow and strong current, and they said, well, okay, it's going to look something like a river. Okay, but that's because they didn't have observations of what the Gulf Stream really looks like, which is something like this. Okay, so it's not like a river. It starts off kind of like a river, but then it becomes unstable and it sheds into eddies and filaments and lots of instability processes, which are very important for mixing traces and momentum. All these models are simplified models. They are toy models to try to understand the main characteristics of the wind-driven gyres, but of course they don't depict the whole reality of the system. What you should have is a non-linear and a time-dependent model to get a more realistic solution. Okay, but then it becomes less tractable analytically. Okay, so now we'll do a simple demonstration of why friction is important in these models. Okay, and these are models that assume the need for friction, but actually if you look at more advanced, more realistic models, you will see that friction is actually not needed. But in the Stommel and Munch problem, friction is needed because of the assumptions that were made. So a simple way of seeing this, and you will see what the solution is. So you take the simple wind-driven solution. Okay, and these are streamlines. And let's say that this is psi 1 and this is psi 2. Okay, and you can take as many streamlines as you want, and you can put them wherever you want. And so you can consider the steady barotropic flow, which is what we did so far. So no time dependency, vertically integrated or homogeneous, and has to satisfy the conservation of PV. Okay, and so where F is any source of well, you can put the wind stress curl there and friction. Okay? So this is obeying plus some friction. Okay? So now this is friction. Okay. Where Q has now been defined to be psi plus the beta y. Okay, and that's the dV. Okay, so you can plug that in, and you'll see that you will get to this. So this is a steady barotropic or barotropic flow. Okay, so because it's steady, the d by dt goes away. So this is obeying, the system is obeying this equation. Okay? So now what we can do is integrate this over an area A, which is going to be this, which is bounded by two streamlines, psi 1 and psi 2. Okay? And you can choose the streamlines that you wish. So we want to integrate this over that area. Okay. And it's a no divergent flow. Okay. So you can get to this because it's not divergent. Now what you can do here is use the divergence theorem, the two-dimensional divergence theorem. Which is simply, so this is going to be my here I put F, but that's confusing. My psi, whatever. Okay, so that if you remember the divergence theorem, it goes from a surface integral to a line integral, where this delta A is the bounding curve of the area. So if you use the two-dimensional divergence theorem, what you get to is psi 1 minus okay, it's just the line integral of the bounding the surface A, which is bounded by psi 1 and psi 2. But now you know that this unit vector n is normal to the streamline. Okay. So that means that un is equal to 0. Okay. So this is going to be equal to 0. But this is equal to the curl of tau, sorry if you can't see, plus any frictional term. Okay. So the curl of tau over the area A, so the vertical integral of the curl of tau here doesn't go necessarily to 0. Okay. It could, but usually doesn't. So this term is not equal to 0. So the only way to make this, the left-hand side, 0 is that these two balance each other. Okay. And the curl of tau, we said that doesn't have to be 0. So now you can take these streamlines, whatever streamlines you wish. Okay. you can pick any streamline and do the same exercise, integrate over the area bounded by two streamlines. You can put them close together, you can put them far apart. The result is going to be the same. So what it means is that in order, and you can take them as close as you wish, so almost the same streamline. Okay, so you can pick the streamlines to be very, very close to each other. So basically that surface A is going to be very, very small. So what this means is that given that the left hand side is equal to 0, basically every streamline or a very, very tiny infinitesimal surface A, in every surface A, the curl of the wind stress will have to be balanced by the frictional effects. Okay? And so what this means is that every streamline has to go through the boundary layer. Because you can choose the streamlines as close as you wish, so you can imagine that psi 1 and psi 2 become almost the same one. And so that means that those streamlines will have to go somewhere where frictional effects are important in order for those frictional effects to balance the input of vorticity by the curl of the wind stress. So if you imagine you are a streamline, if in this region the curl of the wind stress is giving you an input of vorticity, you will have to go through some area where frictional effects are not negligible, like in this place, okay, where you can balance the input of vorticity that you have gained somewhere else. Okay. And so the nice result here, or the nice idea, is that every streamline goes through the frictional boundary layer. So if you look at this solution, okay, you know where the frictional boundary layer finishes. Frictional boundary layer finishes here, and the frictional boundary layer here in the Mook model finishes here. So that every streamline goes through the area where frictional effects are important. Otherwise, if there was a streamline closed outside of the boundary layer, there would be no place during that trajectory where frictional effects are important. And so there would be no way for that streamline, or along that streamline, to balance the input of vorticity. It has to go through the boundary layer where frictional effects are important. Okay? So most of the time, frictional effects here are not important, they're not dominating, okay? But it has to go somewhere where actually that input of vorticity can be balanced by some frictional effects. Okay? It's just a simple way of visualizing why you need friction in the Stommel and Mook model. Okay? This is not reality, it's given these assumptions. And now that you see a numerical solution of the Stommel and the Mook problem, you know exactly where the frictional boundary layer finishes. Okay? Is where the last of the smallest streamline closes. Okay, so when we did the Mook problem, we just started off by saying this was the Stommel problem, he added inner bottom drag, and Mook just added lateral harmonic viscosity, and then we derived the solution for the interior and for the boundary layer, okay? Which is a little more complicated the solution. Okay, it's less intuitive. But you can get to the same solution. You can get to the Munk problem just starting from the primitive equation, okay, which is probably more intuitive, and you see where the lateral horizontal viscosity is coming from. So we can write the momentum equations. Let's say we start from the beginning, and then we will derive the solution for the Munk problem. Okay, so you have Coriolis, you have the pressure gradient, and here we are adding a lateral viscosity coefficient. And the vertical that we used already. Okay, so this is for the x component. Okay, the y component, and then continuity. Okay. So the important thing here is the introduction of the lateral viscosity that we didn't have before, that we neglected always from the beginning, especially when we're doing the Ekman layers, right? We said this is much smaller than the vertical component, so we're just going to use the vertical component. But now we're adding horizontal viscosity. We take a vertical integrated solution, so we vertical integrate the pressure term from Z to minus H, bottom, phi Z. Then we integrate U, Z to minus H, rho naught U. So this is going to be a mass transport, and we can get rid of the rho naught, and V Okay. And so if we do that, and we vertically integrate our momentum equations, the vertically integrated meridian velocity and the vertically integrated pressure field plus AH Flushing view plus Z minus H, this is now the vertical component, d by dz of AV du dz, Z, and then Fu Okay, it's just the vertical integration of the momentum equations. And then we're going to say du by dx plus dy. And this is because we set the vertical velocity to be equal to 0 at z equals 0, z equals minus h. So there's not going to be any vertical velocity at the top and the bottom. So the vertical integral is going to be 0. Then we remember how we defined the stress tensor. If you remember how we defined the stress tensor right at the beginning, taking fluid mechanics as well. At z equals 0 minus h, and the same thing for the meridional component. Okay, so this is the definition of the stress tensor. But if we're talking about the surface stress tensor, we know that the value at z minus h is going to be 0. So we just have a component at the top. And so what we're left now is minus f, the vertical integrated meridional velocity, minus the vertical integrated pressure field, plus the horizontal Laplacian, plus now this is d by dz of av, the vertical integral of that is tau x, plus tau y. And again, continuity. Okay? Now you do the same thing that we always do. You take the curl, or you take the curl of the momentum equations. Okay, so you do d by dy of this one and d by dx of that one. So that's d by dy minus d by dy of f. So that's beta v. And then here you have d by dx of that one, which is okay. So taking the curl now means you do 2 minus 1. Okay, so this minus that one is f d by dx plus dv by dy minus that one, so it's beta v bar. This minus this one goes to 0. So you have this, and you have the Laplacian of dxv minus dy u plus okay. This is 0 because of continuity. This is the vorticity, and this is the curl of tau. And you can plug in the definition of the stream function, and you recover the solution that we know, which is the curl of tau plus you put the stream function here, and you get a quadratic term. So this is the Moog problem. Okay, much easier to get to the Moog problem this way. So we started from the momentum equation, and the important thing was adding the horizontal viscosity term, which we neglected before. So you add the horizontal viscosity term, you vertical integrate, you set the vertical velocity to be 0 at the top and bottom, so continuity reduces to this. Then you define the stress tensor as we always define it. So tau is some coefficient A vertical du dz, and the contribution at the bottom is equal to 0. There's only a contribution at the top. And so we get to this expressions for the momentum equation. You can take the curl of this. So you take the d by dy of this one and d by dx of that one minus the other, just take the curl, and you recover the Moog model, okay, which is including biharmonic friction, lateral, and aside. Okay, so this should be in equilibrium. The last time I did this was a year ago, so if it doesn't work out, we can repeat on Wednesday. So I spent, I think, 2 days in getting the right, well, we'll talk about this. So we found out that there is a western boundary layer, and therefore a western boundary current, and therefore that the wind-driven jars are western intensified, because if you remember, we have a weak interior transport and then a much stronger boundary current which opposes the interior. Okay, so this is telling you that here V is going to be small, and here V interior and V correction is going to be much larger than V interior. Okay, and that's why the Gulf Stream and the Kuroshio are much faster and much stronger currents than the one that you can find at the interior. It's just because they have to return the same mass within a narrow western boundary. Okay, so we found that principally through a mathematical solution, and at some point we had to choose a mathematical solution that would put the boundary on the west or on the east. And then when we were doing the boundary correction during the asymptotic matching, we saw that the boundary solution could only decay towards the interior if it was on the west. If it was on the east, the solution would grow towards the interior. So that didn't make sense because of our assumption, and so we chose the western solution that would decay towards the interior, right, if you remember. And so that solution was mostly dictated through, let's say, a mathematical derivation. But you can understand the presence of a western boundary current simply by looking at potential vorticity conservation. Okay. Which again is not the reason for a Western boundary current, it's just a way of balancing vorticity. Okay. Okay, you have the PV equation and you just need to balance planetary vorticity. So whenever planetary vorticity changes, relative vorticity will have to change in order to conserve vorticity, assuming that h is a constant. Okay. So if h is a constant, in our model there's no topography, h is a constant, then if there is an input of vorticity, either f will change or relative vorticity will change. So actually something that we never discussed is that if we found an interior solution and then we said, okay, then there's going to be a boundary current that returns the flow, but who said that the boundary current had to be a boundary current? I mean, we didn't know that it was a western boundary or an eastern boundary. It could have been a middle boundary. Right? Doesn't make much of a sense, but perhaps you could have found a solution to that, especially given that we started with the Stommel model that wasn't putting friction on a side. So if you put friction on a side, you immediately think of a frictional boundary layer. Okay? But the Stommel model was putting friction at the bottom. So you might have thought that there was a bottom boundary current returning the mass, for example, in a vertically integrated model. So if you think again of the simple wind stress curl that we're always using, that is providing an anticyclonic input of vorticity, okay, in the subvertive interior and in a subtropical gyre in the northern hemisphere, but it doesn't make any difference. When the wind causes Ekman pumping, the water columns are squashed. Remember the schematic of the wind stress curl, anticyclonic in the northern hemisphere, providing Ekman pumping and squashing down the isopycnals. If the isopycnals are squashed, then in the interior solution relative vorticity will not change. It will not start spinning faster or slower in its own place. But what the entire interior ocean will do is move towards the equator in order to lower planetary vorticity. There's an input of vorticity. This is not going to change, so F will change to balance vorticity. So we are so the interior solution is in the northern hemisphere. The interior solution is to move towards the equator in order to conserve vorticity. And so by moving towards the equator, F decreases. Somewhere there will be a return flow, which could be on either side. Let's imagine we didn't derive the solution yet. It could be on either side. And there, when there is the returning part of the circulation, you are moving back to higher latitudes. So where F, so you're changing F and you're increasing F. And there must be some forcing that puts back higher vorticity into the fluid and has to balance this increase in F. It cannot be in the form of planetary vorticity, because we said already that in the interior solution is planetary vorticity that is changing. In the frictional boundary layer is not, we did the scale analysis, is not F that changes, will be relative vorticity to change. So the input of vorticity has to affect relative vorticity, okay, this one. And that's why you have a frictional boundary layer on a side. So let's imagine the two possible solutions. Okay, so consider a western boundary current in the northern hemisphere, subtropical gyre, with friction between the current and the sidewall. Okay, so let's imagine this. So in the interior, you have an input of vorticity. Okay, and if you look at a western boundary solution, which is this, okay? In the northern hemisphere, what you have is an input of vorticity in the positive sense, and this is negative into the ocean. Okay. And this one, because of the hand rule, is positive. Okay. So you would get this input of vorticity. So by having a sidewall, what happens is that you reduce the boundary current velocity to 0 at the wall, and that was the Munk problem. Okay, U is equal to 0 and V is equal to 0 at the wall. Those were the two boundary conditions. So the boundary current has positive relative vorticity. Okay? And this vorticity is injected into the fluid through the friction at the wall. And that allows the current to move northward towards higher Coriolis. Okay? You're moving north, so you're changing F. How do you balance that change in vorticity? Is by changing relative vorticity. Okay, so the two balance each other. Oops. If, on the other hand, the narrow jet returning flow to the north were on the eastern boundary, so you are now on this situation, you will have a negative input of vorticity into the system. Okay? And that is not balancing the input of vorticity, the negative input of vorticity within the interior. There's an input of negative relative vorticity that cannot balance northward boundary current. So this solution is not permissible as a balance for southward Sverdrup interior flow. So if you want to conserve vorticity, and in this case you are injecting some negative vorticity into the system, the only way of balancing this negative input of vorticity is through a western boundary current that balances that vorticity by changing relative vorticity. Okay. So you can use simple vorticity arguments to see the need for a frictional boundary current, okay? Because you have an input of vorticity, and within the interior you can balance that by changing F, but in the boundary layer, if you have to return that flow where F is changing, the only way of balancing that change in vorticity is through relative vorticity. And it has to be on the western side, because on the eastern side it doesn't balance this vorticity. You can do the same exercise, and it would be nice if you do it, because last year it was an exam question. You can go through the same exercise for a subpolar gyre, for example, so it changes. Instead of having a negative input of vorticity, you have a positive input of vorticity. And you can go in the southern hemisphere, okay? Have an anticyclonic wind stress in the southern hemisphere. How do you balance that input or removal of vorticity? Is by going towards the equator or towards the pole. And how can you balance that change in vorticity in a boundary current? You can only balance that change in vorticity in a boundary current if the boundary current is, you will see that it's always on the west. It's always a western boundary current, whether you are in the northern hemisphere, in the southern hemisphere, whether you have a subtropical gyre or a subpolar gyre. And if you look again at this very, very simple schematic of surface time mean climatological surface currents in the ocean. You see in red subtropical gyres, you see in blue subpolar gyres. Okay, they go, subtropical gyres, they go this way in the northern hemisphere, they go the opposite sense in the southern hemisphere, and you see a thick red arrow, which is the returning boundary current, and it's always on the west, in the northern hemisphere and in the southern hemisphere. And you can use vorticity arguments to see that that boundary current has to be on the west. Okay? So now we're done and we can start again. I will close this because it might not work. I'm ashamed.